Hello everyone, welcome back to Calculus 1, and this time we are still working on the so-called optimization problem in section 4.7. And indeed, there are 6 steps according to the textbook. But as I'm saying, if you want, you can follow strictly. But I hope you see the general idea to solve such a problem, okay? You do need to read and understand the problem clearly, and then you will have to convert the actual situation into a mathematical problem and then solve the problem mathematically and then make your statement how to fit the number with the actual situation. Okay, and even for the example I just finished, I have some steps combined, but anyway, hopefully you see the idea how it works. How about let's move to next example. Next example, it is still from the textbook. Indeed, usually I just take examples from the textbook. So in case if I miss anything on the notes, or you still can find out the right answer, and if you needed to see details, or as I'm saying, if I miss anything, you can find everything on the textbook. So this one, it is still a maximum problem. And what we are considering here is this time we are going to build a cardboard box. Okay. And this is actually a practical situation. Usually to build a cardboard box, we start with a single sheet of cardboard. And then don't make it complicated, make it simple. Okay, we consider the following situation. Say we are given a rectangular cardboard. And the way for us to form a box, we just simply cut some squares off, one square off from each corner. And then we fold along the edge of each side. And then, as you can tell, that is the way how we form a rectangular box. And we don't need to consider cover. And we don't need to consider those details, how to connect the edges together to make the box stable or to make the box look pretty, those things. We just want to solve it mathematically. Okay, so the thing is, well, there's not. I hope you see, if that's only the requirement, I say you cut a square off from each corner and then fold along the edge of each side, and then you can make a rectangular, open top rectangular box. I hope you see there are many different ways to make it. This is certainly one shape could look like, and also I would say you could have a rectangular box which may look very tall, but anyway the base somewhat not too big at all, right? So there are many different ways to build such a box, and the actual situation we want to solve here is what size square should be cut out of each corner to get a box with the maximum volume. Okay. So in this case, as I'm saying, before you get started, you really want to give a try if you are convinced you have many choices. I say at least give a try 3 different choices, 3 different ways, and you will see the volume of each box will be different. And then for me, I don't want to make it too complicated. Basically, I'm still following the steps outlined on the textbook. But anyway, as I'm saying, I don't necessarily just follow step 1, step 2, step 3, one by one. I have some steps started to combine it together. Okay. So this is what I'm considering. First part, we are having a rectangular cardboard, a piece of rectangular cardboard. It is 25 inches by 36 inches. Then cutting a square off from each corner. And then, as I'm saying, the drawing part of actually I copied the drawing from the textbook, really. And this drawing looks very nice, right? Looks like it's a perfect rectangular box. And indeed, that's all we are considering. Okay, there's no top. Certainly there's the bottom part, and there's no cover at all. Open top rectangular box. Okay, so this is the situation, and I did use the notation because we really need to consider the size of the square. So I simply say the length of the square, it is x. The length of the square, it is x. Okay, and then I have step 2, step 3, and 4 combined. Basically, they just require we need to calculate to find out the maximum volume of the box, of the rectangular box possible. So I'm looking at the rectangular box clearly because the size of the length of the square is x. Now you fold this side up, and it turns out to be the height of the rectangular box. It is x, right? And then you think very carefully if this 24 minus 2x makes sense to you. Look at this part. Basically, this is how 24 minus 2x is generated. Because we are cutting a small square off from each corner. So along this side, there are 2 squares off, right? So we are going to reduce 2x, subtract the 2x from 24 to get the remaining length, the length for the remaining part. So that is 24 minus 2x. And very similarly, we cut 2 squares from the top and the bottom along this side. The remaining length would be 36 minus 2x. And then, I hope you understand somewhat, we do have the length, width, and the height of this rectangular box. So indeed, the volume, it is a product of the height times the length times the width. So it is to maximize the volume. That's the objective. Okay. And also for this problem, as I mentioned here, if you look at the mathematical equation, indeed, it may have multiple solutions. So this time you want to understand clearly, according to our arrangement, clearly the length of x cannot be too big, right? If you cannot have 24, that will take the entire thing. That means that you are just throwing away the entire cardboard. And indeed, x cannot be even greater than half of 24. You are looking at the both sides. So somewhat the bad, well, I mean, in the extreme case, if you want to cut this entire thing off, you cut 2 squares of length 12 inches. I'm saying the length of x cannot go beyond 12. Cannot be 12 at all, really. Cannot be 12 or bigger. It will have to be less than 12. So this is very important. And hopefully we'll see why we have this part of discussion. Not only mathematically it could be of anything, but anyway, according to the actual situation, x clearly has to be positive, and besides, x will have to be less than 12. Okay. And then step 6, actually, this is the most important step. To find out the maximum or minimum, we are going to use derivative, right? And also, before you work with the derivative calculation, in this case, you want to know this is product of 3 functions, 3 factors. And certainly, you could use product rule 2 times to get a derivative. But anyway, my choice here is I multiplied this product out first. So this is how I get the product. It's a 3rd degree polynomial, right? X times x times x, that's going to be x cubed. Okay. And indeed, I mean, in this case, the multiplication is really not that complicated. The easiest way would be multiply those 2 terms together. And then you get a trinomial. Then each term multiplied by x. So this is how I did it. Okay. And then after multiplying out the function, and then we figured out the derivative. It's rather easy. Okay, using the power rule. And also I did, first 4. This is carried from the first round of the function. Okay, 36 and a 2, there's a common factor 2 there. 24 and a 2, I can take out another 2 as a common factor. So there's a 4. Okay. And then from the calculation of the derivative, inside those 3 terms, I'm seeing 3 as a common factor. So you take out the 3 as a common factor, which will making 4 and 3 together as 12, times x squared minus 20x plus 12, plus 72, I'm sorry. And usually, this is really to find out critical point, it is to solve this quadratic equation, right? And usually, we solve quadratic equation use the factorization. But anyway, not in this case, it cannot be factored. So you really want to consider to use the quadratic formula. The quadratic formula gives us 2 solutions, 10 plus 2 times square root of 7. Then 10 minus 2 times square root of 7. As I'm saying, you don't want to jump to the conclusion. You tell people to get the maximum volume of the box. In such a case, you cut a square of 10 plus 2 times square root of 7, or 10 minus 2 times square root of 7, 2 times square root of 7. Maybe there are 2 answers, and indeed it's not correct. Remember, in step 5, we mentioned to fit the actual situation without doing the actual calculation. I already figured out x cannot go beyond 12. And for the number here, 10 plus 2 times square root of 7. Square root of 7, I think it will have to be at least 2.5, right? Then 2 times 2.5, that would be 5. 10 plus 15. X, if you take the number with a plus sign, x really it is bigger than 15 or bigger than 12. And we realized earlier it's not possible. So indeed, in the end, I realized I'm saying the only answer, the only arrangement we can make here is to make the length of the square 10 minus 2 times square root of 7, not a plus. Not a plus, okay. So when you cut a square of this size, and for sure the volume of the box will be maximized in this situation. We are working on optimization problems, and optimization problem usually involve with a maximum or minimum. And so far, we did 2 maximum problems. And also, we could have a minimum situation. So my last example, maybe let's take a quick look how the minimum situation would look like. Okay, this is also from the textbook, Minimizing Surface Area. And I really want to say you want to consider example 33 and example 37 together, because somewhat a similar situation, but anyway, we are doing different things. Okay, let's take a quick look about this 4.37. This time we are still having a rectangular box involved, but anyway, just believe it or not, the rectangular box, it is already built. You don't worry, well, how you make this rectangular box. Okay, it is already done, and it has a given volume. It has a given volume. It has, it was built, but I mean, it has a given volume. It cannot be of anything else. It will have to be 216 cubic inches. And then you want to decide what should the dimension of the box be to minimize the surface areas. The surface of the box. Surface area of the box. Okay. So in this case, well, I still have some drawing here. And you may want to know, supposedly the box, we don't have to worry about how the box it is built in details. The only requirement here is that we just want to make sure the volume, it is 216. So in this case, actually, the rectangular, the box here, it has a square base. Okay. So I said x, it is the length of the square base, of the square in the base. And y, it is the height. And then clearly this time you want to understand, we want to minimize the surface area, right? So let's take a look how we find out the surface area. So it has open top. No area from the top. There's area from the bottom, that's x squared. And also along those four sides, there are four sides, right? So the area would be, because the bottom, it is the base, it is a square. So all those four sides are the same. One side, the area one side, it is x times y. So all four sides, 4 times xy. Okay. Our goal this time it is to minimize the surface area. And then, well, this is really a function of two variables. So you want to make sure if you can convert this function of one single variable. And read the problem again. It says, whatever the box, it doesn't matter how we build it, and whatever the box you may have, the volume of the box will have to be 216 cubic inches. So what you need to consider here is you simply need to do the calculation. The volume would be the area of the base times the height, which means x squared times y is 216. And solve for y from here. So y is 216 over x squared. And clearly about the restriction for the x, and you could figure out a little more details of x. But anyway, let's give a try, skip some details. But anyway, as I'm saying, at least we can tell x will have to be positive. The negative answer won't work here. Okay. And then step 6, we get everything into a function of a single variable. The surface area, it is calculated in this fashion, but y can be replaced with the formula in terms of x. So indeed, we are having function in terms of x. In terms of x only, right? And then to find out a maximum or minimum, we just calculate the derivative. We find out the critical point. We find out the critical point and s prime. And indeed, the critical point I found here, it turns out to be the third root of square root of 432, and which can be simplified a little bit, 216 times 2. The key root, the third root of 216, I suppose that's 6. 6 to the power of 3, that's 216. So x, it is 6 times the third root of 2. And then accordingly, you can find for y. Y is 3 times third root of 2. Okay. And then, as I'm saying, you really want to go through little details if you are convinced. For me, I just put this on the notes. From the first derivative test, I say the surface area is minimized. Okay, when we have this choice of x and that choice of y. X is the 6 times the cube root of 2. Y is 3 times the cube root of 2. And also you can calculate the minimum area. And it need, I think it should be 108 times the third root of 4. So this is about the example. The last example I want to present in this section, 4.7. 4.7, it is a discussion of optimization problems, and usually an optimization problem will involve with a maximum or minimum. And I think we did the examples with maximums. There are 2 examples about maximums, and the most recent one we just finished, it is about the minimum. It is about the minimum. So thank you for watching. I'll see you next time.